Hello, today's space engineering lecture covers the topics of concept of operations and interface definition. The intent of this lecture is to give you an overview and the importance of concept of operations and interfaces. So this is really an introduction. It is not all the details you would need to do all of this, but it does show you the importance in early system engineering and system design about these two topics. So, concept of operations versus operations concept. And it's often interchangeably used, but they're not the same in space system design or NASA. So, concept of operation is developed early in pre-phase A concept studies by the technical team. It describes the overall high-level concept of how the system will be used to meet stakeholders' expectations, usually in a time sequence manner. It describes the system from an operational perspective and helps facilitate an understanding of the system goals. It stimulates the development of the requirements and architecture related to the user elements of the system. It serves as a basis for subsequent definition documents and provides the foundation for long-range operational planning activities. An operations concept is developed much later in the design process, like in phase, in the critical design or preliminary design part of the phase. And it describes how the flight system and the ground system are used together to ensure the concept of operation is reasonable. So it's really a more of a getting ready for flight and lays out the specifics of how the operations will be conducted. So you may have crew timelines as well as additional details about the execution of the mission. So it is really a detailed timeline of the operations, the mission operations. This might include how the mission data of interest, such as engineering or scientific data, the the objectives are being captured, returned to Earth, processed, made available to users, and archived for future reference. It is typically developed by the operations team much later in the design process. So the difference being a concept of operations or ConOps is done in pre-phase A to write the story of the mission and how the mission capabilities and so on, the functions will be used and to do the mission and the design concepts to some degree. You may not even have all the designs yet laid out or designed, but you have the idea of the functions and capabilities needed to execute the mission. Again, operations concept is really about the flight, the mission, the flight of the mission, and the specific details of that operations. So where does this fall into? It is the aspect among the design process, and it really shows up in the trade studies and iterative design loop, where you have the functional and logical decomposition of functional requirements and understanding of high-level requirements that now feed into a description of how you're going to execute the mission. It takes into account the capabilities and some of even the early conceptual designs and even the different scenarios, the mission design reference mission scenarios that you may be looking at. So it is part of this initial step of defining a project. It establishes, you work through the vision, mission, goals, and objectives and stakeholder analysis, at this point, you begin to develop your concept of operations, which really talks about how you are going to execute the mission, what you are doing there, what is the purpose of the mission, and what is it that you're doing. Here it shows up that a part of, and I briefed this lecture previously on stakeholders' expectations, and it is one of the outcomes where you do your knowledge capture of the stakeholders' expectations and those derived or allocated requirements. So again, when you talk about concept of operations, think about the human spaceflight operations, those 5 areas that we talked about previously: the crew operations, internal to the spacecraft, the external crew operations or EVA, the mission operations, the science operation, and logistics and maintenance. All of this needs to be discussed and talked about and documented in the concept of operations document that talks about the whole mission and how you plan and what you plan to do. Of course, the concept of operations would include these architectural elements, depending on your mission and what the objectives of the mission are. But typical architectural elements include crew return vehicles, deep space habitats, space exploration vehicles, surface vehicles, EVA capabilities, propulsion systems, power and generation systems, thermal rejection, deep space communications, docking, robotics, logistics and spares, maintenance and repair. And so all of those items would be talked about in this concept of operations: how they're being used, what are the crew doing, what are the robots doing, walking you through this scenario in a written format. Also included this, you may dive down into that concept of operations and talk more about specifically the exploration habitat subsystems. So you may cover to some extent what these subsystems are or what you're thinking they might be, or even future work to do trade studies between different avionics or power generation systems, etc. So here's an example of a commercial crew concept of operations. It shows a launch vehicle launching. So this is your design reference mission chart. It shows the separation of the crewed vehicle, the capsule, in low Earth orbit, its rendezvous with space station, its departure from space station, and then its entry, descent, and landing here back on Earth. And typically it also lays it out how many days this looks like it's taking. So what would it include? What does it encompass? It encompasses a description of activities of the pre-launch, description of the activities during launch, description of activities during LEO, during the ISS rendezvous and docking, a description of the activities while you're on ISS or doing the mission, and what the vehicle is doing in quiescent mode if that is the case. It's a description of activities pre-vehicle departure, a description of activities during departure and pre-orbit, a description of activities during deorbit, a description of those activities during landing, and then a description of activities post-landing. So really, this is an encompassing document that is a forcing function to make you think about all the different aspects of the mission modes, and description of those major elements. For example, the ground system, mission control, launch vehicle, flight suits, commercial crew vehicles, ISS, landing and recovery systems. All of this is incorporated into the concept of operations. So let's talk about design reference missions. And this is an example of a design reference mission chart. And a couple important aspects of the chart and how to use it is that you typically lay the launch vehicles are on the left, and there's Earth, or it could be, in this case, it's Earth at the bottom and the moon at the top where the mission's taking place. It could be Mars, it could be other destinations. So you have your launch vehicles. And I also like to think about this, an important part of this is the mission modes. As part of this mission mode analysis is thinking through what is going on at each one of these mission modes, from the aspect of performing the ground processing, performing the launch, performing LEO loading, and any docking or rendezvous that may occur, the translunar injection, what's going on there, the disposal of the stage, translunar injection stage, the transfer or loiter to low Earth orbit, to then to LOI to low lunar orbit, and then transfer down to the lunar surface. You perform the surface mission, science and mission objectives. Then you depart. You have your rendezvous in orbit, and then you come back to Earth. So looking at each one of these different mission modes is a forcing function to think through what is the vehicle doing, what is the crew doing, what are we doing back here on Earth in mission control, et cetera, et cetera. So you want to touch base on what is going on and who's doing it and why. And that's part of the analysis and understanding of a concept of operations. So this was previously kind of focused in general. Here's a little bit more detail on a crewed mission phase. Again, walking through all those different steps of the mission modes, doing the analysis and understanding what is going on. These design reference missions are often used without all of the red callouts, but I think it is informative to have these callouts and also talk through them. This is an example of a cargo mission where it's a delivery. It's no crew and there's no return. So it's a one-way delivery of cargo to the moon. And again, you would walk through the mission modes. So as part of your concept of operations, it's important to include both crew and cargo modes and what is going on during those modes. This really helps you to understand the lander concept of operations, the performance of that lander, what's going on, what your assumptions are about the lander, etc. Another way to show, and this is often used, and I've used it numerous times, is to have the concept of operations as a flow chart like this. And you have it simple, high level at first. And this is a TransHab, example of the TransHab concept of operations for installing and outfitting it. So at a high level, and the black area marks means that if you were to double click this, it goes down into more detail, and the icon shows here. So then you can decompose and go in more and more detail about what does it mean to assemble and check out the flight vehicle. You know, ship the TransHab to process at KSC, perform TransHab installation and preparation at KSC, install TransHab into the orbiter payload bay, launch, remove and install, deploy, inflate, complete the vestibule jumper connections. The crew enters the TransHab and outfits it and gets it ready for occupation. So at a high level, this is a concept of operations, similar to what we previously saw here, but in this format. And this is actually quite useful because you can dive down into each one of these areas, and I'll show you, that really begins to define and describe and talk through what's going on, what the equipment needs to do, what the crew's doing during all this time, what even space station and the ground crew mission control is doing. So when you think of TransHab functions, these are all the functions that incorporated into TransHab. And so from this standpoint, the concept of operations would include this. So if you're talking, have a concept of operations, talking about the aspect of the system, the TransHab system, and also the launch and deployment and outfitting. You would also include the functions, all the functions that are incorporated into TransHab. So another aspect about, so that really kind of covers the concept of operations in, at a high level, giving you an understanding of what its use, how it's used, and when it's used in the system engineering process. As part of that is also identifying interfaces, the interface definition process. And this is important early on to begin to understand the ins and outputs of the systems between different components and between subsystems and between systems and elements. So interface definition is an important part of this process. And so it helps to define the interface requirements, which is really important. It is important to define all interface requirements for the system, including those to enabling the system. So including external interfaces form the boundaries between the product and the rest of the world. You also have internal interfaces that could be within a habitat as well as the external interfaces. And it's important to walk through and think of them. And so what type of interfaces are you thinking about? What should be included? Operational, command and control, computer to computer, mechanical, electrical, thermal, data, human interfaces, and so on. And there's mechanical interfaces, there's secondary structure, there's primary structure, there could be docking mechanism interfaces, etc. So one useful tool in defining interfaces is a context diagram, and that's in Appendix F of the NASA Systems Engineering Handbook, which depicts the product in all of its external interfaces, and it could be internal as well. So once the product components are defined, a block diagram showing major components, interconnections, and external interfaces of the system should be developed to define the components or interactions. And this could be done in a number of ways. One typical way is like an N-squared diagram, where you have all the system components and you look at them individually. Do I have an interface? Do I have a need? Do I need power? Do I need data? Am I sharing power? Is a power system or a power switching unit? Are you required to send power to specific devices and sensors? You know, the sensors all have interfaces, both data, etc. So this N-squared diagram, basically, it can be done in Excel, it can be done in a number of things, but it's a matrix representation of the functional or physical interfaces between the elements of a system at a particular hierarchical level. So you could do this elements to elements, and then you could do it just as a single element. And then within the element, you could begin to look at the systems or even the subsystems. So you can go at different levels to break down those interfaces. And you really need to dive down all the way to the bottom of all the different interfaces to truly understand the flow, the interconnectedness between the various components and subsystems. N-squared diagrams have been used extensively to develop data interfaces, primarily in software areas. However, it could be used to develop and understand hardware interfaces and human interfaces as well. So the system components are placed on a diagonal, and the remainder of the squares in the N by N matrix represent those interfaces. And I'll show you that in a minute. So the square at the intersection of a row and a column depicts or contains the description of that interface between the two components. It could be also represent the flow, which direction data is flowing, or power, or whatever, the mechanical interface, and so on. So for example, a solar array has a mechanical interface with the structure, and an electrical interface and a supplied service interface with the voltage converters. Where a blank appears, there's no interface between those respective components. So here's kind of that example. You've got components running down through here on a diagonal, and then you're identifying between component A and component B. You have a mechanical interface. You also may have an electrical interface between B and A, and also D and A, and D and B. So you can see you can have multiple types of interfaces connected to them. So this is one way to go through that diagram and begin to define those interfaces and what type of interface, electrical, mechanical, supplied service, etc. This is another example of a different way to do it, in which case you can see here we've got structure, fuel pods, thrusters, solar arrays, heat converters, etc. And then as you each line across here connects to each one of these. So if you follow structure connection here, all the way back over to here to the gyros, you can start to follow the connection, and you can follow the connection between structure and solar arrays, structure and voltage converters, etc. And then you can begin to, in each one of those boxes, identify that connection. What kind of interface? Is it a mechanical interface? Is it an electrical interface? Something else? This is a launch abort system example that I pulled from a project, the AA2 system. And it's a little bit different way to look at the interface. But what they did is they put the range safety, flight ops, ground ops, um, the abort testing booster, the separation ring, crew module, and the launch assembly system, a launch abort system, excuse me. And then they looked at the interfaces between each of them. Between the crew module, obviously they're directly touching, but there's also between that and the ground system. And so you can see the flow. There's a flow that they are providing data and electrical wiring and so on back to the ground system. There's also that feed that comes from the ground system to it. So you can begin to map out and understand these different interfaces. Once you have identified the interfaces, then you can begin to talk about what's the quantity of the flow at that interface, how much data, how much electric power, voltage, watts, etc. So you can begin to really understand the inputs and outputs and flows, and begin to model that, and begin to model the system and look at simulations and run simulations using these interfaces. And if you miss an interface, you'll know because the system won't close per se. This is an example of the TransHab interface. It really lays out between Node 3 and TransHab the dependencies between the two. So there's a wireless antenna that goes both ways, structural mechanical interface, both have dependencies on that, data back and forth, thermal back and forth, audio, video, etc. Now, in this case, you can see the oxygen and nitrogen actually only flow to TransHab, not back. So it's a one-way delivery of that service. And on the other hand, wastewater was actually flowed back to Node 3 for processing, because there was no processor on TransHab because it was part of the ISS system. And so you can look at the different aspects and they go back and forth. And this is an example of an interface diagram that would be included in an interface control document, an ICD. This shows the common berthing mechanism, the bulkhead, and shows the different connections and penetrations on that bulkhead and the different services and where they're connected and what's used and what's not used. This is very important because, when you connect to like Node 3, you need to make sure that the jumpers between the different elements, the different vehicles have the right setup and know the right flow from the interfaces. And then you can actually create a table that supports that, going by the discipline or subsystem and the type and the interface location. This is a simple example of an interface diagram between the FGB module and a power data grapple fixture. So you have the power data grapple fixture assembly over here, the FGB module structure over here, and the mounting structure. And then, so what do you have? You have the A and B power legs feeding the power data grapple fixture. You have structural mechanical, thermal, EVA, and environments. So external system interfaces for habitat systems, structure, ECLSS, thermal, power, and communications are all kind of external interfaces that a system would have or together. And so you would have, like for a habitat system or element, you'd have element to element interfaces and element to surface if it is on the lunar or Mars surface. Structure, you could have station, vehicle, or surface infrastructure. ECLSS could be external water or oxygen tanks. Thermal, you could have the external thermal radiators for heat dissipation. So you're going to have pass-throughs of the thermal fluid going to the radiators. Power source, you're going to have pass-throughs again from the power source, power generation source into the habitat. And course, communications is very similar. You would have probably a hard data line from your communications dish into the habitat. This is just a rough diagram talking about the interconnections between all the different aspects of the internal habitat and then the external system. So you can see that you have different aspects of structure, communications, external systems, thermal control, power generation, and airlock or EVAs. And EVA could be internal as well, but you do have an interface to that environment, to the exterior. And then interior, you have all the subsystems, and not necessarily all of them are listed here, but you can see it as an example. The human and crew systems have a lot of interconnection between data management, primary structure, secondary structure for handholds and restraints, environmental control, power distribution, et cetera, internal communications, and so on. So there's a lot of interconnectedness and interdependencies between all these systems from an interface perspective. So that's all I wanted to give you a brief lecture on, the concept of operations and interface definition. Thank you very much for your attention.